I'm Brian McCass, and I was the design lead.
I'm David Montgomery, and I was the technician.
I'm Steven, I was the scribe of justice. This is lab, spirit collaboration, and we're at lab 2A.
So I'm going to talk a little bit about the setup before we start with all the other material. First, of course, we started with the laser as usual. This time it's only on a translation stage in the Y, and it's perpendicular to this rail. We use two rails, so we need to reflect the beam, and we do that by using a mirror. We chose not to use the pentaprism for ease. And the mirror is attached to two translation stages, one that's on the optical axis for the big rail, and one that's in line with the laser. Over here we have our three main components, and that would be the Hartmann hole. It has 11 holes, each equally spaced by 1 millimeter. And then we also have where we put the lens. We use three configurations: the plano-convex, concave plano, and then just the bi-convex. And then of course we have our microscope objective.
So more about the setup is that we wanted to choose a numerical aperture that allowed for no vignetting even at the extreme edges of the lens. And so what we did is we said that we have a 1-inch lens here, that's 12.7 millimeters, and 100 millimeter focal length. And we calculate the theta here, and from that we were able to put it into the formula here, Na equals sine of theta, and we found that we need at least a 0.1260 numerical aperture, and we had a 0.25, so we were within the correct numerical aperture. For the next part of the lab, what we did was we had the microscope at marginal focus, and we moved through all the Hartmann holes on the Hartmann mask. And we got data similar to this. This is the ray fan. And as you can see, at 0 we have defocus because we are defocused from paraxial focus. And this is the ray fan that we're going to get. I'll show you on the computer now. Okay, and similar to the board is what we have here. You can see that it's flipped from what we have on the board. That's because it depends on where you define your first marginal focus. It's just semantics, really. And here they are, and you can see they return to the same point here, and they have a 0 in the center, and it's got a slope in the center that tells us defocus.
Alright. I don't know if we're
Just go.
Alright, so what we did for this next part was we were trying to find preaxial focus in relation to marginal focus, and we did this by translating along the z-axis with the Hartmann mask, different points. And so you can see we have two marginal points and one preaxial. And so how we did this was down here with the Hartmann mask, at the edge points, this would be our marginal focus points, and so they would focus to the marginal point, and a preaxial point would focus here. And so you can see from the graph up here that that's what these points down below correspond to, and we'll show you our results that we got in lab. Alright, so these are our results for the lab. You can see it looks kind of parabolic. We know we had some amount of defocus due to the shifting of endpoints here. We have about a 0.2 shift, so that probably corresponds for our defocus.
3.
Now looking at the actual setup, for parts C and D, for the marginal focus, we basically concentrated on using the axis perpendicular to this optical axis and moving the mirror for the Hartmann mask. So if you zoom up real close, you can see that by going to the very extreme right or left sides, that would be our marginal focus. And our preaxial focus we found would be in the center, which that experiment was done by moving this translation stage that is in line with this optical axis.
Go.
Just to add in, theoretically, the marginal focus from the left or the very right hole on the Hartmann mask should be in line, and you shouldn't have to touch this. But in our case, it wasn't perfectly in line, so we had to choose which one was closest, and for us, it was the right hole.
3.
So for parts C and D, we made sure that we had the plano side first, and then the convex side on the other side, which was hit second. That's what caused defocus with spherical aberration. But in the last part, we got to play with shape factors. So basically, we turned the lens around, and when we plotted everything out, we basically saw just defocus and minimal spherical aberration. Pause. So this is the formula for finding shape factor, which is B. Basically, you just look at the curvatures of both sides. Since we only worked with plano and convex, we just worked with zeros and 1. So for the whole thing, we compared the shape factors of 1, 0, and -1. And we saw that with the shape factor of 1, we got the least spherical aberration and probably the most defocus, which we can see on the computer. So for a shape factor of 1, you basically just see a linear line, which basically represents defocus when we look at a plot from -1 to 1. So this was our plot when we used a biconvex lens, which has a shape factor of 0. As you can see, it's not as linear as when it was just 1. For the shape factor, you can see some curving, and the data kind of gets askew at the end because we weren't able to plot the data since we ran out of micrometer spacing.